Hello everyone, welcome to another F-sharp Essential Lectures. And today we will be continuing to with the I think one of the last sessions, the Computation Expressions sessions. Today we will be covering fundamentals and also compound effects. And last week we covered object programming in F-sharp and recursion. And yeah, so we have been running these lectures for now 11 weeks. So if you are new to these lectures, please visit our website, amplifyingfsharp.io, F-sharp Essentials. And on here you would find the scheduled times as well as the previous sessions where you will be able to watch the previous videos. So yeah, as you can see, all of them are here, so you can watch that at your own speed. If you are also on YouTube, you can visit our YouTube channel, where in the playlist you will find a dedicated playlist with all the sessions. So yeah, without further ado, I will hand over to Ian so we can start the session for today.
Can't share my screen. You need to stop sharing. Thank you. So, welcome to session 11. So the primary reason for this session is computation expressions. We'll get onto that in the second half. So what we're going to cover today is going to do a quick recap over session 10. So we're going to go back over some of the object programming stuff that we did and the recursion, and then we'll have a look at computation expressions and a little bit behind the hood. Not too much. This is I look at this course more as things that you want to use rather than things that you want to deeply know. If you really want to deep dive into them, there are good sites to do that, and there are some good blog posts as well on building computation expressions. So let's start with a recap on last session. So object programming. Obviously, F-sharp's a functional first language, but there are times where objects and classes make absolute sense. So if you're dealing with lots of .NET libraries, a lot of those are written for objects. So it obviously makes sense sometimes to fit in with those if you have to. Other situations are things like if you want to encapsulate some state and hide it from other things, then that's a good way of doing it. And also if the data structures that you want to store are different than what you're exposing to the outside world, a class is a good way of doing that as well. So a quick look at class types. So this is a simple class type in F#. So it's a type just like a record type, etc. But the core difference here is that it has a parameter list. In this case, it's an empty parameter list to start off with, and then it has members, and the members expose the public interface. Shouldn't really use the word interface, but it is the public contract with that particular class. So in this case, we've got a class called FizzBuzz that takes no parameters when it's set up. That's the primary constructor, and it has a member called Calculate that takes a value and then converts it to a string. Obviously, I haven't done all the logic here yet, but I'm going to do that. So I'll better put the type in, so it looks a little bit neater. So to create one of those, we just create it with the constructor. We don't need to use the new keyword. The new keyword is only used really when you have an iDisposable, in which case you do need to use it. It's the compiler will tell you anyway. And then I can just quickly call it. So I just create a simple list of 1 to 20, and then I'll do a map over the list and just calculate each of those. So I know that works, but it obviously doesn't calculate FizzBuzz at this time. So what we'll do is we'll copy this little function that I've got down here on this little bit of code. So we'll get it to work. So I'm going to create a little internal function called calculate. Doesn't need to be called the same thing, but that's just what I've decided to use. Let's line all this up. And if we change that to calculate with a small c, I have no access outside of the class to this small c calculate function. So scope, there is scope involved in this in terms of visibility. So if I now run all of that again, that should hopefully work. So that works. So that's a simple definition of a class. We can then add interfaces. So in this case, I've added an iFizzBuzz. You don't need to use an I with it. That's just convention within .NET. You don't actually need to do that at all. So the definition of the interface is that the function you're defining in this case is abstract, and you're defining the signature of the function. So it takes an int and returns a string. In this particular case, I've added a parameter to the constructor, which is a mapping, which in this case is a list of tuples of. Let's sort this out then. So that's a tuple of int string, and it's a list, just to be explicit. And we put the interface in here, so we use interface, the name of the interface with, and then we've got the member underneath. And if we scroll down, we do exactly, we create the FizzBuzz instance, and we pass in the mapping that we want. We notice we've now got a problem. So the type FizzBuzz does not contain the field constructor or method or function calculate. Okay, the reason it doesn't do that is because the calculate function is on, sorry, the calculate method is on the iFizzBuzz interface, and F# doesn't implicitly convert in this particular situation. So what we need to do is we need to explicitly convert FizzBuzz to iFizzBuzz. So we use the upcast operator, which is colon and greater than, and then convert it to iFizzBuzz, and that now works. Okay, you use interface exactly the same as you use them in C#, so you can use them as inputs to functions, as parameters in functions, exactly the same. Object equality. So this is a class type GPS coordinate, and it takes latitude and longitude, and we've got simple properties. So they're read-only properties there. And if I create those and then compare them, they're not the same, because classes in F# are exactly the same as classes in C#. So they use reference equality. So they're not the same instance, therefore they're not the same. So to get around that, we have to do exactly the same as they do in C#. So you have a series of hoops to loop through. So you have so you have to override get hash code and equals, and also you need to implement the IEquatable as well. And we've also overridden we've set the equals operator as well to use this logic as well. So as I said, there's a few hoops to jump through with all of this. But what that then allows us to do is to test equality based on the composition of the data rather than the actual instance itself, the reference of the instance. So that's equality. Encapsulation. So in this particular case, I've got a type which is a recently used list. I'm setting the capacity, and inside I've got a resize array. Now, resize array is the standard .NET list, but obviously we can't use list because list is used for something else in F#. So it's called a resize array in this, and it's generic. So I have internally I have this array, this resize array with data, and I can do things with it. So I have a public interface that I can use, so I can add items to it, and I can get a list of the items out, and that's it. So, and you can see that when doing the same things, I'm upcasting, and you can also downcast as well. So I've upcast to the interface, and then I've downcast using that operator. So that's encapsulation. So as I said, objects are useful for certain things. You're not going to use them all over the place, but for very specific jobs, they are a very useful tool to have. Object programming in F# is a lot more powerful than I've shown in the last session, and within this is just touching at the edges really. But if you're going to go deeply into object programming, F# is probably not the right place to do it. You're probably better off sticking with C#. So recursion. Recursion is a really simple idea. It's a function that calls itself. So this is a simple sum function. It's going to loop round and it's just going to add. So we're going to give it a number, and all we're going to do is give you the sum of 1 to the number that you pass in. So it's a simple loop. So we do a match based on the number that's passed in. But the important thing to note here is that there is a stopping condition. At some point, you need to stop this process. If you don't have a stopping condition, you'll just run out of memory because it can't stop. It will just carry on. So, or it'll throw an exception, which is the general thing that goes wrong. In this particular case, this is a bad thing to do, what we're doing here, because what we're doing is we're actually building up a function as we go, but it can't complete the function, so it can't actually do any calculating until it's reached the stopping point. So what happens is on each iteration, you're basically building a new calculation every time. sorry, it's adding to your calculation. So if you start at 5, for instance, you'll go 5 plus the sum of 4, which then becomes 5 plus 4 plus the sum of 3. But all of these are nested, and it doesn't complete until you get to 1, and the sum of 1 is 1, and at that point it can start summing up all the values. So it's a very inefficient way of doing this. So there is a nicer way of doing it, which is called tail call optimization, and this is a much more efficient solution. So to do that, we need to rewrite our function a little bit. So I'm going to call this sum t. I'll do the same again. Okay, so what's going to be different here is that rather than passing one item in, I'm actually going to pass 2 items in. So I'm going to pass in a and that's going to be a running total in this particular case. So what I do is I match n, so n again is, so if I go with 1, I'll do this in stages. So I'll do 1, I would return total, and otherwise we do sum t of n minus 1 and total plus n. So if we do, so I know this is going to be incorrect, but we'll get to that in a second. So if I do the sum of 10, okay, so I get 54, which I know is incorrect. That's because that's the it should be 55. So what I actually have made well, I didn't make a mistake. I knew that I'd done it. Was that should actually be 0 in this particular case, because 1 is still needs to be added to the total. So your calculation doesn't finish until you get to 0 in this particular case. So it's slightly different than the other one. But the advantage of this is that each iteration is effectively independent, because you have no calculations to do after you do each iteration. So if we think about our sum of 5 again, so we'd go sum t 5 0, and then we'd go sum t 4 5, and then it will be sum t 3 9, and so on until we get to the answer. So this is a much more efficient way of doing it. There is also an attribute that you can use as well, called tail call. That only works when you actually compile it, when you do a proper application, rather than doing a script file like this, because it won't actually do anything in this. And the other thing that I showed with recursion is that sometimes I don't like this. Sometimes what gets passed in and what's used in the loop are often 2 totally different things. So a slightly alternative way of doing this is to is to do it slightly differently. So to not make the main function recursive, but to have an inner function that is recursive. Call that loop. So call that remainder and that one total. So that becomes remainder, that becomes remainder, that becomes remainder. And then I need to start the process. So n and 0. So that's an alternative way of doing this. And that obviously depends on whether there's a difference between what you want to expose to the outside world and what you want to and what you actually want to loop with. Okay, so that's recursion. So that's finishing off where we were last week. So I need to go back to my README. Right, so on to the main thing from this week. So computation expressions. Computation expressions are basically a bit of well, not a bit of syntactic sugar. They're a really nice way of handling effects. So we've been using effects quite a lot. So things like options and result, things like that. So there are 4 built-in computation expressions. So sequence, which we've sort of seen, but I haven't really mentioned it. Async and task. So we obviously haven't seen, we haven't done any asynchronous programming so far. So we're going to do some of that today. And then we also get query, which is the ability to use something to use the link queries. So not the extension method style, but the actual link query syntax. So you can do that inside of F# as well. So there are actually 2 types of computation expressions. We've already seen one of them, which saw the validation computation expression. So that uses the built-in keywords. That's really wrapping stuff around bind. But there's another style which is used for creating DSLs. And what the computation expression system allows you to do is to write custom operators. So there's a series of built-in ones already, and we've used some of those, but not even close to all of them. But you can add your own, and there are some really good examples of this. So I've included 3 there. So Saturn, which is a DSL for building websites. That's a nice little wrapper around Giraffe and ASP.NET Core. You've then got Farmer, which is a something for deploying things to Azure. And then you've got FS HTTP, which is a DSL for HTTP client. So they're really nice uses of custom operators. So you can build DSLs quite easily, but I'm not going to cover that in this particular session. That's very much a it's not so much a niche area, but I think it's an area where you need to be careful. I've built lots of DSLs over the years, and there are a lot of work to keep working properly. So unless they're used for things that are used quite often, I don't think they're worth doing. But the primary job we're going to do them with is with effects, and we're also going to look at how we can combine effects as well. So once you get onto to programming properly, you'll end up doing lots of async, and then there'll be lots of things that return option or result as well. So how do we work with combinations of those? And that's quite a nice way of doing it, because without computation expressions, some of it gets really horrible very quickly. If you want to learn more about from absolute basics and get fairly deep dive into computation expressions. Scott Voloshin's F# for Fun and Profit is the place to go, and there's a whole set of blog posts. There's probably, I think there's about nearly 20 blog posts on computation expressions, so they go into a lot of detail on this. So without further ado, let's get started. Where are we? Options. So I've created a console app here. So just using .NET New Console Lang F#. And I've got one of the examples that we've done a little bit of before. So we've got two functions. We have multiply and divide. And then we have a calculate function that combines them together. And obviously we need to use option.map and option.bind to work with these. Actually, there isn't a compiler warning there because I've put option because I've got the map and bind in place. Okay, so this function has a divide followed by a multiply followed by a divide again. This isn't a particularly difficult one, but you have to remember when to use map and when to use bind. So instead of that, we can use a computation expression to do this. So we've got exactly the same two functions, and here we've got a computation expression called option, and we have a let, and that's called a bang operator. So let bang R1 equal divide xy. So what the bang does in this particular case is so divide returns an option. What the bang does is it unwraps that value. So if it is sum of a value, it will unwrap it. If it's none, what it will then do is it will basically skip over the next two lines and won't run them, and will just return none from the function. So as soon as you get the first instance of none in this option, it will return. It doesn't actually return. It will go through the levels, but it hides all of the complexity of knowing about sum and none underneath the covers for you. So it just makes it nice, easy to write. And then if everything works correctly, so if you divide 10 by 5, for instance, we get R1 will be 2, and then we multiply it, we get R2, and then we have the final one there as well. So we have the return keyword, which is only used in computation expressions. So what does the computation expression look like? Because they're not built in. Well, this one certainly isn't. So this is almost the simplest computation expression you can build. So the first thing we notice is the attribute, which is auto open. This is nothing to do with computation expressions. This is just an attribute for modules. So we've already seen requires qualified access, which forces you to use the name of the module before the name of the function. So in this case, where you've got option.bind, there'll be a requires qualified name attribute on that, so it forces you to use option dot, with the bind. What auto open does is it means you don't have to open the module explicitly. It's done for you. So you'll notice that this is a class type. So option builder is a class type. And there are some standard types, sorry, some standard methods that are used on these particular things. So the two important ones they're interested in are bind and return. So this is really working with bind, and return is obviously what comes out at the end. There's also returns from as well. So to be able to use return bang, you need to have a return from function set up. As I said, you don't really need to. We're not going to spend too much time on this because it's more important to know how to use them rather than to understand how they're actually structured underneath, unless you want to get really into them. And the last one is we've said let option equal option builder. What that means is that word, the option, is the thing that we use with the curly brackets. We've got any questions at this point?
Yeah, we had the one. We had the one that I think Jimmy that's in chat already answered. It was about the we can pipe forward in the C where the C is.
Okay. Right. So we can. So as I said, we can define our own computation expressions. And the idea of them really is to simplify working with effects. So in this particular case, we've got a fairly simple set of formulas. So we change. So we'll take this, which has option.map and option.bind that I need to remember how to work with, compared to that. So this, in this particular case, I think is slightly easier to understand. But we'll see as we move on, because this is one of those things where I think it gets better the harder the problems are. So that's options. So let's have a look at result. Let's look at something a little bit more complicated. Result. A few seconds to catch up. Okay, so this is one of the examples we did much earlier on in these sessions. So this might even have been the third session, I think, when we did result. So we've got get purchases, which takes a customer and returns a result of a tuple of customer or decimal and an exception. And then we've got try promote to VIP that takes that particular tuple type and returns a customer. And then you've got increased credit if VIP, which takes a customer and returns a result of customer or exception. And then at the bottom, I have an upgrade customer function that takes a customer and returns a result of customer or exception. And again, we've got exactly the same thing. We've got a combination of things that use result and things that don't. So get purchases returns a result. Try promote to VIP doesn't, and increase credit if VIP does. So again, we've got a combination of functions, and rather than me writing a result computation expression, what I did instead was to load the fstoolkit.errorhandling NeoGet package. which is really good. All of these are written for you. So any effects that you want to work with, so any such combinations, there's probably a computation expression already written for you in that that's designed to work really well. So let's have a look at what our computation expression looks like. So it's exactly the same. The only difference is I have to load the FS toolkit.error handling, and then I've got the result computation expression. So result with the brackets, and then so I use let bang where there's a function that returns a result in this particular case, and I don't need to use a let. I don't need to use the bang when the function doesn't return that. So again, I can do I can use return bang if I want to, rather than the last one. So rather than using let, rather than creating another value, I can just use a return bang. So if I get rid of that. So that does exactly the same thing. So again, I think that's a little more, it's a little easier to understand. As long as you understand what the bang is there to do, there's less typing involved. That one. Right, I said that we'd cover asynchronous programming as well. Oops. So in this particular case, I've got a file I haven't added. Right, so I've got a simple file here, which just contains a little bit of data. I'm not going to import the data. I'm going to look at something a little bit different. So I've created a simple record type that's got the name of the file and the length of the file in bytes. So this is the async computation expression, and async is built in to the async computation expression. So we said there's async and there's task. So async is the original asynchronous programming model from F#. It's a lazily evaluated system, so you can have lots of async things together, and they won't actually run until you actually make a call to use them, rather than they're only evaluated as and when they're needed to be evaluated. So task is obviously the one that C# uses and is part of the .NET framework. So F# can use that as well. So there is a task type now built into F# since version 6, I think it was. It came in. Before that, we had to use a community-driven task system, but task library. But now we don't need to because it's built in. And you can also, in this particular case, you can see here that file.read all bytes async. Although it says async, it's actually, when we eventually get there, returning a task. So async has things built in. So async.await task. So it actually allows you to use task-based code within the async process as well. So in this particular case, because it's async, we've got a bang because this returns an async. So it's unwrapping the value from the async. So that's giving us a bytes array. We obviously pick up the name from the file, and then we can return the record from that. So the only thing that we're doing that's slightly different than most people do is there's this async run synchronously. If you do lots of this, you're doing things very wrongly. There should be very judicious use of async.run synchronously. But in this particular case, the only way for me to get the code to actually run is to use something like that. So we get the file path, we get the file information from that file, we tell it to actually run, and then we print the result out at the end of it. So I'll just do a .NET run. And there you can see that I've got a record at the end, which returns data.csv and length 200. Okay. Right, and on to the bit where it starts to get really interesting. Let's give it a second to catch up, to load the project and put it into F# mode. Right, so this is an example from the F# toolkit.error handling website. So you don't actually get you got the GitHub side of it, and you've also got a lot of documentation as well. And this is one of the examples from the documentation. So this is a function called login, and it uses 4 other functions. So what it's going to do is it's going to take a username and a password. So what it does is tries to get the user from wherever it gets the user from. So you pass in the string with the username, and you get an async user option back. So it's an asynchronous operation, and you may or may not get a user. And in this particular case, you have to, so part of the logic is that that it should return an error if you don't return a user. It then checks the validity of the password, and again, if the password isn't valid, it should report that as an error. And then you should authorize, and again, if it's not authorized, it should stop at that point. And finally, it creates an auth token, which again could cause an error, but you know, it's we need to think about how to do all of this. So what I did was I've put it all into an async computation expression to begin with. So it takes 2 strings and returns an async result of either auth token or login error. So this is a compound effect. So this is quite a common one. So async result or task result is a pretty common thing in business processes. So I started by doing the user try get user, and obviously I need to think about how to handle errors there. The same with the password, if that's incorrect. And you can see there are all sorts of errors and things here. And you could spend quite a lot of time trying to get this to work by going through the things that we already know. So trying to use things like result.map and result.bind and option.map and option.bind, and also the result.map error as well, which we need to use. It takes a lot of effort and a lot of thought to do this. I did this as an exercise, and I ended up with about 30 lines of code, and it looked absolutely horrible. And I just thought, this is this is really bad. I can't show it. It just looks really, really horrible. Even looking at it an hour later, I had to think about what it was actually doing, because it was getting quite complicated. So rather than doing that, what we can do instead is we can use the stuff that's in the FS toolkit.error handling, because it's designed for this particular sort of situation. So if I comment that out, and I'll go and push this back. So within the within F# error handling within FS toolkit.error handling, there is an async result computation expression. So what we have here is the first one is we do a let bang with the user. So we pass the username into get try user, and then we have using the async result module, we have a require sum. And if it's an error, then we return unknown user. So if I go up here, we find that we have specific errors for authorization and for tokens, and then we have a specific set of errors for the login function itself. So if it fails if it can't find the user, then it's an unknown user. Invalid password is invalid password. If it's unauthorized, then it's of that type of auth error. And the token error is a type of token error. So we have specific errors that we're then wrapping up inside the login error. So if this isn't sum, if it can't find a user and returns none, then it will return an error of unknown user. At that point, it won't run, as far as we're concerned, the remaining 3 lines. It will just return error of unknown error. If it succeeds, then obviously we can unwrap the user, and the user comes out here. And we can move on to the next line. And in the next line, we don't actually use the return value. So if we don't use the return value, we can use the do bang or do keyword. And the do keyword is basically the equivalent to using let bang and underscore. But this is a nicer way of doing it. So if you're not interested in the return value from this, but that's only on the positive side. So if you notice, we pass the user in to the is password valid function with the password, and then we have a result.require true. So the reason why this one's result, not async result, is that is password valid is not asynchronous. So it doesn't need the async part. So you just need the result part. And if it's not true, so if it's false, then we return error invalid password. Then we go on to the next line. So we authorize. Since authorize returns an async result, then we need to use async result map error if there's an error, and return unauthorized. And then finally, we've got the last one, which returns a result and not an async result. So again, if there's an error, then we map the error from the specific one that we get from create auth token into the one that we get for log error. We end up with token error. So a problem that may have appeared to be quite complicated, actually, with some help with some really clever people who've put together a really useful library, turns out to be relatively simple to use. So that's all that I wanted to cover with computation expressions. As I said, they're syntactic sugar for simplifying a lot of our logic with effects. So we don't have to remember so much about map and bind in these particular situations, and it becomes much more about writing business logic than thinking about lining things up properly.
Yeah, computation expressions are one of the things that is a abstraction mechanism that that kind of allow you to create your own domain-specific language without really having the language to support many of those. So you can abstract that computation expression that can be a DSL for HTML for anything actually that you want, and as long as you follow the the structure that you show us with the option type, you can basically unwrap things, you can wrap things, you can combine things, and there are multiple different members that you can overload in order to do that. So it's really powerful. But yeah, it's it's one of those things where it's about to be extendable. The language is more, F# wants to be extendable rather than add these on the compiler and add more bloat and more features and features and features.
Yeah, I mean, these are great features if you need them. And the types of applications that I write do need them. So we end up with lots of things that are using things like task result. So we end up using this sort of thing all over the place. And it just simplifies the programming model. It's as I said, it's relatively simple when you've got a single effect, but when you've got a combination of effects, particularly when you've got task or async involved in there as well, it's much harder to reason about your code if you have to do everything longhand.
Yeah, 100%. Yeah.
So it's important that you understand computation expressions, because we will be using them in the next session when we talk about ASP.NET Core. When we're going to be looking at Giraffe as well. So that's it, Edgar.
All right. Yeah. So we have in the amplifying F# blog, we have a entry that we wrote about computation expressions that two of the amplifying F# members gave on the BovConf thing in Germany, I think it was 4 weeks ago. So yeah, please check that out. But yeah, let me share my screen back and we can close the session. So it's going to be this, right? So yeah, thank you, Ian, for this session. So yep, so we have one more session remaining, which is going to be using ASP.NET Core, and we will be using web pages and API. So API would be Giraffe, and I guess for the other one, web pages is that the view engine for Giraffe?
Yeah, It's going to be
Nice.
Giraffe View Engine. Yeah.
Lovely. Yeah, looking forward to that one. So yeah, thank you everyone for attending to the lesson. And as normal, as usual, I will publish the video in a couple of days, and I will update the overall information so you can join next week.